All right, so we're going to continue on filling in various portions of our Laplace transform table and all of that kind of good stuff today. So let's say that we have a time domain function f of t that is equal to cosine omega t plus theta times a unit step function. So for those of you that took me for Circuits 1, you've probably seen this trig identity before. What I'm going to do is use the relationship cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta to express this in terms of things that we've done before, right? So for us, that's going to look like cosine of omega t times the cosine of theta minus sine of omega t times the sine of theta, all of that multiplied by a unit step function. Cosine of theta and sine of theta are literally just constants because our phase angle does not change, right? So that is some constant value. So all we have is a constant value. So let me express it like this. So we could have cosine of theta multiplied by cosine omega t multiplied by u of t, and this will be minus sine of theta multiplied by sine of omega t u of t. And we already know, these are the last things that we covered before we left on Monday, what the Laplace transform of this thing in the brackets is, and what the Laplace transform of this thing in the brackets is. So very easily, our Laplace transform of f of t, based on our prior knowledge, should just come out to be cosine theta of the Laplace transform of cosine omega t u of t minus sine theta of the Laplace transform of sine omega t u of t, and then substituting in from our previous parts on our table, this is going to look like s times the cosine of theta divided by s squared plus omega squared minus omega times the sine of theta over s squared plus omega squared. And we can lump these together to give us s cosine theta minus omega sine theta all over s squared plus omega squared. Very similarly, if we had a sine function in the time domain with a phase angle, so if f of t is sine of omega t plus theta u of t, we can use the trig identity that sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta, which would allow us to express our original function as sine omega t cosine theta plus cosine omega t sine theta all multiplied by a unit step function. And breaking it down slightly further, this would be the cosine of theta times sine of omega t multiplied by u of t plus sine of theta multiplied by cosine omega t u of t. And once again, we already know what the Laplace transforms of the things in the brackets are. So the Laplace transform of f of t, and I'm going to skip these kind of intermediate steps because it's so incredibly similar to our last example. We are just going to wind up having omega times cosine of theta over s squared plus omega squared plus s sine of theta over s squared plus omega squared. And then since I have a common denominator, I can simply add those results together, giving me omega cosine theta plus s sine theta all over s squared plus omega squared. All right. So now let's briefly look at exponentially decaying sinusoids. Just for what it's worth, these are some of the signals that you saw when we had underdamped circuits way back in circuits 2. The response was an exponentially decaying function multiplied by, cosine omega dt plus or minus sine omega dt with some coefficients and all that kind of front. So we're just going to learn the transforms of those. So if we have f of t is equal to e to the minus at times cosine of omega t, no phase angle here to be very specific, u of t. If we treat cosine omega t times u of t as just some generic thing, which we're going to call g of t, we can use the frequency shifting property of the Laplace transform in order to figure out what this is, right? So realistically, we just need to go back into our notes and find the Laplace transform of cosine of omega t. And then everywhere we see s, we replace it with s plus a according to the frequency shifting property. So using that frequency shifting property, then the Laplace transform of f of t is simply s plus a over s plus a squared plus omega squared. Very similarly, if we had an exponentially decaying sine function, so e to the negative at sine omega t u of t, we can do the exact same thing, right? So if sine omega t times u of t is our function g of t that is being frequency shifted, then our Laplace transform should be simply omega over s plus a quantity squared plus omega squared. All right, so you will probably notice I'm going to shift gears fairly significantly here. I'm not going to do any more sinusoidal functions. We're going to have a couple of more transformations that we're going to figure out once we learn how to do the inverse Laplace transform and we learn partial fraction expansion. So we won't see exponential function multiplied by a cosine function with a phase angle, or an exponential function multiplied by sine, also including a phase angle, until we actually work backwards and stumble into those things. Because there is no simple and direct substitution that we can do there. Other than using a crap ton of trig identities to split things down, and then it's not going to be a nice closed form solution anyway. Okay, so shifting gears fairly significantly, let's look at some other functions. Okay. So let's say that we have f of t is equal to t times u of t. For what it's worth, this is what's commonly called a ramp function. So our function just grows linearly as a function of time, and then we would turn it off with a second ramp function that's shifted by some amount. Okay. So if I have some function g of t that I'm defining as just a unit step function, what's the relationship between g of t and f of t? But it's not scaled by a constant amount, it's scaled by an amount that's changing in time. So it's not going to be a derivative, right? The derivative of g of t is the Dirac delta function. Okay. The integral of g of t will be this guy up here, right? So let's think about what that means. If I were to plot a unit step function, it would look something like this, right? So it's 0 until it turns on, and then it's got a constant value of 1, right? So as I integrate this thing with respect to time, I'm just integrating dt, which is just going to look like t. And then because it turns on at 0, I tack on my unit step function to make sure that it doesn't exist before t is equal to 0. So this function right here is literally just the integral of this function right here. So that means that f of t is simply the integral of g of t dt, and wouldn't you know it, we have a time integration property of the Laplace transform as well, right? So what's the Laplace transform of g of t? It's in your table, we did it yesterday. 1 over s. What does the time integration property of the Laplace transform tell us to do? So an integral in the time domain is equivalent to what? Multiplying by a factor of 1 over s. So 1 over s times 1 over s is 1 over s squared. So the Laplace transform of this function is just 1 over s squared. So let me write it as 1 over s times g of s, which is just 1 over s times 1 over s, or 1 over s squared, okay, using the time integration property. Goodness. So let's say that we're interested in a function f of t that is t squared u of t. So we can do something pretty similar, right? We're going to wind up using the time integration property. So what should my g of t function be? So where when I integrate it, I would get this thing right here. So effectively, what's the derivative of this thing? 2t, right? So if I had a function g of t that is equal to 2t u of t, I can play around with this a little bit, right? So what would happen if I scaled time for a unit step function, right? So we have a time scaling property effectively saying I'm stretching out the time axis. Does that impact a unit step function in any way whatsoever? Not at all. A unit step function is one from 0 to infinity. It doesn't matter if I increase my scale on the time range or compress it. It's still just going to be one forever, right? So this 2t times u of t could be written as 2t times u of 2t to make this variable the same thing as this variable, so that effectively I just have this guy again with my new variable as 2t, which would allow me to write my Laplace transform using my integral relationship and all that kind of good stuff. So this is nothing more than effectively just some function g whose variable is 2t, which means my original function is the integral of g of 2t with respect to time. So I could use, so all I'm doing with this g is just saying it's a function that's different than f. That's all that that g means. I may be misunderstanding your question. But they're the same thing.
But if you put 2t in the first one, you will get 2t, you get 4.
I think I understand what you're saying. So what you're saying is if I replaced this t right here just with a factor of 2t. All right, so let's call this h of 2t then. Who gives a shit? All right, so we'll put an h there and we'll put an h here. Just to be more clear, I understand what you're saying there. Okay. So what we should wind up getting is the Laplace transform of f of t will be 1 over s times the Laplace transform of h of 2t, effectively. So what's the Laplace transform of this guy right here? So it's going to be 2 over s squared, because we're multiplying the t by a factor of 2, so it should be double whatever this thing is. Another way to think about that, so we would have 1 over s. So let me go back to my notes here really quickly so I make sure I'm talking about the correct property. So we are going to use the time scaling property, right? So the time scaling property is what lets us take the Laplace transform of this thing. So we would have, from the time scaling property, 1 over our scaling factor of G of S over 2, which comes out to give us 1 over S multiplied by a factor of 1/2 multiplied by a factor of 1 over S over 2 squared, all coming out to be 2 over S cubed. So when I divide this guy by 1 over S over 2 squared, that's putting a 4 in the numerator. 4 over 2 is where this 2 comes from. And we can keep this process going. So if we had some function f of t is equal to t cubed u of t, or some function g of t that is, let's see, so that would be 3t squared u of t. I could write that as 1/3 of 3t squared u of 3t, right? Because 3t squared will give me 9t squared divided by 3 gives me this guy over here. So now I have the same effective variable. So we could call this 1/3 h of 3t like so. And then our original function is just 1/3 h of 3t dt, and we're integrating that thing. So finding this Laplace transform is going to look like 1/3 times 1 over s times 1/3 of g of s over 3, which is going to look like 1/3 times 1 over s times 1/3 times why do I have a 2 in my numerator here? Sorry, let me just 1 second. Oh, I'm dumb. I have a 2 in my numerator there because I'm doing this thing right here. Sorry. So 2 over s over 3 squared, like so. So let's just be really clear about what's going on here. That one should have been cubed. There we go. Sorry about that. All right, so I have a 3 cubed in the numerator. And then I have effectively 3 squared in the denominator. So I'm going to have 2 times 3. And then I will have an s to the 4th power in the denominator. So 2 times 3 over s to the 4th power. So can we notice a pattern? Right. Exactly right. N factorial over s to the n. 100%. You guys could probably just look that up, but it's way more fun, in my opinion, to figure out how all this crap works. So generically speaking, based on the pattern that we have observed, or that you guys got bored of my bullshit and just looked up on the internet, generically speaking, if I have a function that is t to the n u of t, its Laplace transform is n factorial over s to the n plus 1. All right, just a couple of more of these before we can get to the inverse Laplace transform fun. So let's say that we have f of t is equal to t to the n times e to the negative at u of t. This is just a frequency shifted function, so we're just going to take this guy and replace s with s plus a to get our Laplace transform. Easy enough. All right. Got 1, 2, 3 more to go. All these are fairly straightforwardish. So if we have f of t is equal to u of t minus capital T, so this is just a times shifted unit step function, then we can use the time shifting property. Time shifting property is take the units, take the Laplace transform of the unshifted thing and then multiply it by a factor of e to the negative s capital T, right? So using the time shifting property, this should simply become 1 over s, so that's the Laplace transform of the unit step function, and then I multiply that by e to the negative s capital T from applying the time shifting property. If I have a time shifted ramp function, so t minus capital T u of t minus capital T, what should my Laplace transform be? So what's the Laplace transform of the unshifted ramp function? 1 over s squared. So it's just going to be 1 over s squared times the same e to the negative st. And the last one that I'm going to do with you guys for today is a time shifted, frequency shifted unit step function. So we are just going to apply the time shifting and frequency shifting properties simultaneously. So what should our Laplace transform be? Should be this guy. Everywhere we see s, we replace it with s plus a. Right? Because that's what the frequency shifting allows us to do. So 1 over s plus a e to the negative s plus a, I believe. Okay, so I've bored you guys enough with the Laplace transform. So now I'm going to shift gears and bore you guys with the inverse Laplace transform. So let's say that I have a frequency domain function 4 over s plus 2 plus 6 over s plus 5 squared plus 8 over s squared plus 4s plus 5. And I want to figure out what my time domain function would be, which is effectively just taking the inverse Laplace transform of this. Instead of doing those convoluted complex integrals, we can simply use our table. But we will at times need to be a little bit creative, okay? So I'm going to break this thing down into smaller little pieces, right? So I'm going to call this F1 of S. Let's call this F2 of S. And let's call this F3 of S. So the inverse Laplace transform of F of S, according to the linearity property of the Laplace transform, should just be the inverse Laplace transform of F1 of S plus the inverse Laplace transform of F2 of S plus the inverse Laplace transform of F3 of S. So from here, I want you guys to use the table that we've developed and tell me what the inverse Laplace transform of 4 over s plus 2 should be. And to make things a little bit easier, this 4 in the numerator is simply a constant, so I could rather easily pull that out. So this would look like 4 times the inverse Laplace transform of 1 over s plus 2, right? So what's the inverse Laplace transform of 1 over s plus 2? E to the negative 2t, u of t, right? So this is going to give me a 4e to the negative 2t u of t. Nothing particularly mind-blowing there. We can do something fairly similar. The inverse Laplace transform of f2 of s would be the inverse Laplace transform of 6 over s plus 5 quantity squared. Once again, because that doesn't look like something super familiar, I'm going to pull that 6 out. Inverse Laplace transform of 1 over s plus 5 quantity squared. So what do you guys think? T e to the negative 5t u of t multiplied by a factor of 6, right? Let me just double check here. So this thing right here, right? So I'm using this guy right here, okay? So I have an s plus a thing to the second power. So that means n must be equal to 1. So 1 over s plus a to the second power is this guy right here where n is equal to 1 and the a is equal to 5 based on our parameters. So we would have 6t e to the minus 5t u of t. All right. And then lastly, inverse Laplace transform of f of 3 or F3 of S, would be the inverse Laplace transform of 8 over S squared plus 4S plus 5. Exactly right. So we could factor the bottom, right? But this doesn't factor super easily, right? So what I mean by that very specifically is if we applied the quadratic equation to that thing, we wouldn't get like +2 and +4 or something like that. We'd get wonky numbers. As a matter of fact, anyway, what we can do though is we can break it up into something that makes a little bit more sense. So let me explain what I mean by that. So this would be the same thing as the inverse Laplace transform of 8 over S squared plus 4S plus 4 plus 1. Right? Because this 4 plus 1 is just 5. And that is something that I can easily factor, right? This is nothing more than S plus 2 quantity squared. So I'm going to come down here. So this is the Laplace or inverse Laplace transform of 8 over S plus 2 squared plus 1. Okay. So what do I have that has a denominator that looks something like this? So the e to the negative at sine of omega t kind of thing, right? Where in this case, a is going to be 2 and omega is going to be 1, right? Because we can always say that 1 is the same thing as 1 squared. So this to me looks like 8 e to the negative 2t sine t u of t. And putting all of this together, the inverse Laplace transform of our original function f of s is just going to be 4e to the minus 2t plus 6t e to the minus 5t plus 8e to the minus 2t, sine of t times u of t. So this process is fairly straightforward. I say fairly, we did have to get a little bit creative with a couple of things, but it is fairly straightforward if our function f of s is expressed as the sum of a series of smaller terms that have well-defined inverse Laplace transforms. So now let's break everything and consider relationships where we don't have the sum of a bunch of easily defined things, okay? And so that's going to take us into what's called partial fraction expansion or partial fraction decomposition. How many of you guys have had to do this before in your 245 class? Okay. I don't remember how your math class teaches you to do it. Based on the feedback that I got last year, my batshit insane way seems to get the same answer and it's easier to understand. So hopefully that's great. We'll see if I can pull it off again, okay? So let's look at partial fraction decomposition. And we're going to look at multiple cases here, okay? So let's say to start with that I have some function in the frequency domain, f of s, that is of the form. So I'm going to have some numerator up here, s to the mth power plus some constant k1 times s to the m minus 1th power plus k2 times s to the m minus 2 all the way out to k sub m s to the 0, which is just a hippie fancy way of saying some constant term. Okay. Over a polynomial s to the n plus c1 s to the n minus 1 plus c2 s to the n minus 2 all the way out to some constant term c sub n s to the 0. Okay. So these k sub something are all just constants, right? So we have no coefficient for our highest order term in the numerator, and then there's a coefficient for the next lowest term, and so on and so forth. And any of these k's can be zeros if we just don't have that term. Same thing here. This capital C1, capital C2, and so on and so forth are just the coefficients of this nth order polynomial in my denominator. So I have effectively some function n of s for my numerator and some function d of s for my denominator, where I'm going to put the constraint here. So where n is greater than m, okay? Not greater than or equal to, greater than. Now, to be clear, in this class, I will never give you something where m is equal to n. If you had that in your math class or something like that, you could use synthetic division to lower it down to some constant plus a polynomial of this form for whatever worth. But I'm not going to make you do that synthetic division crap, because this, as much as it looks like it right now, is not a math class. Okay. So this is our generic thing. All right. So whenever we have a system like this, we can decompose it into smaller order terms, okay? So let's consider something relatively easy where we have something that could be factored, okay? So let me use an explicit example here with numbers and everything. Let's say that we have f of s is equal to s squared minus 4s plus 3. I think that's something that we can factor relatively easily over s cubed plus 4s squared plus 3s. So somebody factor the numerator. Why is it taking so long? S minus 3 times s minus 1, right? Am I mistaken? And if you don't believe me, you can use the quadratic solver on your calculator to get that result very quickly. But we should have s minus 3 times s minus 1. Factoring the denominator, what should we get? S times s plus 1 times s plus 3. So none of these terms in our numerator can be canceled out by any of these terms in our denominator. So we've just got this big gross thing right here, right? So what partial fraction expansion or partial fraction decomposition allows us to do is to split up something like this into the following form, okay? So we will have some number a1 over s plus some number a2 over s plus 1 plus some number a3 over s plus 3. So we have decomposed this thing down into the sum of smaller parts, which will all hopefully have a much easier inverse Laplace transform to apply, right? Based on just this thing right here, right? Whatever A1 is, so we're going to have some constant times the unit step function plus some constant times a factor of e to the negative t times the unit step function plus some factor times e to the minus 3t times the unit step function, right? So we can go from whatever our denominator is here, just break it down into bits, okay? Just to be super clear here, I guess I should have tucked this in. So this is a special case, sorry about this, where we have distinct real poles. Sorry for missing this. So what I mean by distinct real poles is, okay, so let's talk about what a pole is. Sorry, I'm a little disjointed here, okay? So when we have a polynomial like this, we have what are called poles and zeros, okay? So a zero is effectively any value of s that makes the numerator 0. And a pole is any value of s that makes the denominator 0, okay? So for this particular thing right here, we would have zeros of positive 3 and positive 1. And we would have poles of 0, negative 1, and negative 3, right? Because if s is equal to 0, the denominator goes to 0, and this thing blows up to infinity. Whenever s is equal to negative 1, this part goes to 0, the whole denominator goes to 0, this thing blows up to infinity. Whenever s is equal to positive 3, this part of the numerator goes to 0, which means f of s is 0 as a whole. So that's how we determine our poles and zeros and all of that kind of good stuff, okay? So for this particular thing, we have distinct real poles, meaning that none of these pole values are repeated. So 0 is different than negative 1, is different than negative 3. If we have repeated poles, we will have to modify our process. So we're starting from the easiest possible case first. All right, sorry for not providing you guys that context, okay? So these coefficients A1, A2, and A3 are our expansion coefficients of the system, and the s plus 1, and s plus 3 terms are the pole factors of the system. In order for us to determine the value of any of our expansion coefficients, just those constants, we can simply multiply both sides of f of s by the pole factor of that expansion coefficient, and then evaluate them at the pole value of the pole factor. That's a bunch of words. So effectively, all I'm saying is a sub I, so this is just whichever expansion coefficient we're interested in, will be equal to s plus p sub I, where this the pole value for a particular pole factor, multiplied by our original function in the S domain, evaluated at s is equal to negative p sub I. So to put this into application and have this make a damn bit of sense to you guys, okay, if we wanted to calculate the value of A1, which is corresponding to my pole factor of just s by itself, what I'll do is I will multiply my original function, right? So my original function, I had it factored to be s minus, let me change the order slightly, but it doesn't really matter, s minus 1 times s minus 3 over s times s plus 1 times s plus 3. There's my original function, so that's this bit right here. I'm going to multiply it by s plus my pole factor, which in this case is 0. And then I'm going to evaluate this thing at s is equal to 0. So notice this guy and this guy cancel each other out. I have remaining 0 minus 1, which is -1, 0 minus 3, which is -3, over 0 plus 1, which is +1, and 0 plus 3, which is +3. So I believe that my coefficient A1 is just the number 1. To do A2, we're going to take our second term here, so s plus 1, so that's what we're multiplying by on the outside. Take our original function, s minus 1, s minus 3, over s times s plus 1 times s plus 3, and we're going to evaluate this at s is equal to -1. Okay? Which means this guy cancels this guy, and so we're going to have -1 minus 1 is -2. -1 minus 3 is -4. -1 by itself, because we're just replacing s, and then -1 plus 3 is +2. So that looks like +8 over -2 is -4. Yes. Because my rule tells me to evaluate it at negative of the thing that sets it equal to 0. So effectively, if I have s plus 1, I want the thing, the negative of that number, effectively. The thing that makes it blow up. Yes. So you guys tell me what my process for determining A3 should be. So I'm going to have s plus 3 on the outside, multiply by the whole thing, evaluate it at s is equal to -3. Absolutely right. So this guy cancels this guy, and I should have -3 minus 1 is -4, -3 minus -3 is -6, -3, and then -3 plus 1 is -2. So this is going to be a positive number. 4 times 6 is 24. 3 times 2 is 6. 24 over 6 is +4. So taking these things into account, f of s is then 1 over s minus 4 over s plus 1 plus 4 over s plus 3. And therefore, the inverse Laplace transform of our original function is 1 minus 4e to the minus t plus 4e to the minus 3t u of t. I have another example here, but it's roughly the same thing, so I'm not going to bother with it. We're going to move on to the next thing. Are we okay with this process for distinct real poles? All right, so now let's see what happens for repeated real poles. Okay. So let's say that I have some generic function that could be expressed as some numerator polynomial And then we would have s plus p to the mth power, right? And we still have the constraint here that the order of my numerator polynomial has to be less than the order of my denominator polynomial. Okay. So we could use partial fraction decomposition to get a result where we would have some coefficient b1 over s plus p plus some coefficient b2 over s plus p squared, sorry, all the way out to some coefficient b sub m divided by s plus p to the mth power, where our coefficient b sub m is found by multiplying our original function f of s by s plus p to the mth power, and then we evaluate this at s is equal to negative p. For our b to the m minus 1th coefficient, what we're going to have is, and I'm doing this way so that we can see a pattern, 1 over 1 factorial times the derivative with respect to s of s plus p to the mth power times f of s close these braces, evaluate it at s is equal to negative p. For the b to the m minus 2 coefficient, that's going to look like 1 over 2 factorial. We're going to do the second derivative of s plus p to the mth power times f of s, close it, evaluate it at negative p, and so on and so forth. So just the last one I'm going to show you guys, b to the m minus 3 would be 1 over 3 factorial multiplied by the third derivative of s plus p to the mth power times f sub s. S is equal to negative. So on and so forth. So, as a relatively quick example, let's say that we have f of s is equal to s squared plus 3s plus 3 over s plus 3 to the third power. So the first check that we have to make always is to make sure that the order of our numerator is less than the order of our denominator. So this is a second order polynomial. This is going to be a third order polynomial. We're good to go. We don't have to do anything fancy there. Goodness. So ultimately, we're going to wind up having some constant b1 over s plus 3 plus some constant b2 over s plus 3 squared plus some constant b3 over s plus 3 to the third power. That's our goal. Using our expression up here, so the first thing that we're going to solve for is b3. We solve for the highest order one first. We're just going to take this function, multiply it by the denominator effectively, and then evaluate this guy at s is equal to minus 3. So we should have s plus 3 cubed times s squared plus 3s plus 3 over s plus 3 cubed evaluated at s is equal to -3. Very obviously, this guy and this guy cancel each other out. So we get -3 squared plus 3 times -3 plus 3, which comes out to be, so let's see. So -3 quantity squared is +9. -9 plus 3 is equal to 3. So that's our first one. B2. Let me scroll back up here, right? So hopefully we can see from this first example that when I multiply my original function by the denominator, effectively the only thing that's going to survive is the numerator. So all I'm going to do is I'm going to take the first derivative of the numerator with respect to s, multiply that by 1/1 factorial, and evaluate it at s is equal to -2. Okay, that's all my process should be. So what is the derivative of s squared plus 3s plus 3 with respect to s? 2s plus 3. Evaluate it at s is equal to -3. And we have 2 times -3 plus 3. So that's -6 plus 3 is -3. B1, take the second derivative of the numerator. What's that? 2. I need to multiply that by 1/2 factorial. So what's 1/2 factorial? 1/2. So what's 1/2 times 2? 1. What is 1 evaluated at s is equal to -3? Still 1, because there ain't no s's left, right? So let me just put out here 1/1 factorial, 1/2 factorial times 2 evaluated at s is equal to -3 gives us 1. And then we would simply plug these in, right? So f of s would be written as 1 over s plus 3, -3 over s plus 3 squared plus 3 over s plus 3 cubed. So what would our inverse Laplace transform be? So e to the -3t, that's the easiest one. So -3t e to the -3t. All right, what's next? So let's go back up here really quickly. So we're using this guy right here, effectively, right? Because we have an s plus 3 to the third power, so n is very obviously 2. So we have an expectation of having a factor of 2 factorial or 2 in the numerator. Our numerator isn't 2, it's 1. So we need to cut this thing in half, effectively, in order to make it work out. Right. Oh, no, you're right. There was a 3. Okay, sorry. There was a 3 on top. So we'll take that 3 and divide it by 2 to make it work out. You're right. I thought there was a 1 on top, but anyway. So 3 halves. T squared e to the 3t all by u of t. Let's stop here. The next thing that I want to talk about is if we have a combination of distinct real poles and repeated real poles, but that's really just applying both of these methods at the same time. And then after we get that sorted out, we get to deal with complex poles and then repeated complex poles and all of that kind of fun stuff, which is where we'll get the inverse Laplace transform of those exponentially decaying sinusoidal functions that happen to have phase angles. Yes. Fantastic question. So I think we can cover the remainder of inverse Laplace transforms on Friday, which means we should start actually using the Laplace transform to analyze circuits the following Monday. So I am thinking that the absolute earliest that I would give you guys your test. Let me pull up a calendar here really quickly. The absolute earliest it could possibly be would be the 4th. My preference would be the 7th. Yes. So I'm going to give you guys a homework assignment today, just dealing with Laplace and inverse Laplace transforms, but it's not going to be due until this Tuesday because we haven't covered all of the material yet. I'm just trying to give you extra time to do it. And then when we start covering circuit analysis here on the 30th, I'm going to assign another homework assignment about circuit analysis using Laplace transform, which would be due probably Saturday, just to give you guys enough time to do it. And then I think having the test on the 7th would be the most reasonable thing, so that you have time to, synthesize the information that I'm throwing at you. So that seems reasonable to me, so that's what I'm going to say.